logical layer, as I said in the beginning, performs various calibration and training tasks, such as it will initialize the link state and do the training. It will, manage the exchange of the sideband messages. Although we're not going to do it today, it can also scramble and generating various training patterns. In case there's any failure in the channels, it can do interconnect redundancy mapping, like it will use the spare lanes instead of the main ones. And there are various features like, in case some part of the lanes are not functional, you do a lane reversal, or you use only a portion of the lane, and so on. Okay, there's a lot of functionality required for the logical layer, but today we'll mostly focus on the part that will do the calibration and training of the parameters for the electrical layer. Okay, so again, these models are all provided, and within the same package, there is a subdirect called logical, and to run any simulation inside it, you go into the directory named TB and run the simulation. Let me do that. So I can now turn this off. I'll just run the simulation while we're explaining. And okay, so here is the UCIe model. And we'll go into the logical layer, logical directory. And well, this model subdirectory contains all the models. And the measure curves directory contains all the, module performing the coverage checks. And the last one, TB subdirectory contains various test benches we're going to run to verify the functionality of the logical layer model. Okay, and among them, I'm going to try to run the one that runs relatively fast, which is TB val vref. And to run any simulation, you can simply type make run sim. Okay. In our demo today, we are using Xcelium. I forgot to mention that. Because XMODEL is not a standalone simulator, it's a plugin. Okay. It's a plugin that enables Xcelium to do additional analog modeling and simulation. Okay. So the simulation didn't run because I forgot to source some setup file, which actually defines the location of the channel model, which are used part of this simulation. So I forgot this step. Okay, do this. Okay, I'll let that run. In the meantime, I'll explain how we model the physical layer. So as I said, the physical layer is made of the logical layer and the electrical layer. So the top level model for the physical layer is basically just combination of two. Just have a bunch of wires connecting between them. Now we need the logical layer. And the logical layer consists of three big components. The biggest one is the one in the middle. It's called the link training FSM. So that is that giant FSM that I talked about. And turns out this FSM will do a lot of most of this the task performed by the LTFSM involves test trial, the data transmission through the main band link using a PRBS, or generated by the LFSR, the linear feedback strip register circuits. So there is a part that will generate the PRBS. There will be the part that will validate the PRBS. So basically, this logical layer has the functionality of our PRBS gen and measure BR primitives because it has to perform its own PRBS test. Okay, so the top layer, the top level model of the logical layer will contain these three blocks. Okay, and since LFSR pattern generation in comparison is relatively simple, we'll focus mostly on the LTFSM part. And if you look inside the LTFSM, it's a big FSM performing various tasks right here. We describe it in a more of a hierarchical structure. You can call it a nested structure, that there is one top level FSM, and each state, it can enable a sub FSM that has its own state. And when it's done, it will return back to the top level of FSM, go to the next state, maybe that will enable another sub FSM. And sometimes some of the sub FSM will branch out into another sub FSMs. Okay, and so it's this very big model, and it will take a lot of effort to complete it. And for your easy reading, all of our FSMs are written in the same style, so that once you figure out how you write one of the FSM, it's easy for you to understand the other FSMs as well. Okay. So as I said, a lot of the tasks done in the LT FSM involves this process called point training. There are two kinds of point training. One is transmitter initiated. The other is receiver initiated. The only difference is that who initiates it. But what it does is it will initially exchange sideband messages so that, oh, I want to start the point training. Then each side, our specs calls one side a main module, the other one calls a partner module. So each side will get ready. For example, it can reset the pattern generator. It can reset some of the, let's say PLL, DLL, DCC, and so on. And then once everything is ready, the transmitter side, the main side, will start sending patterns. We'll start sending those PRBS patterns. And then at the same time, receiver will receive them and check if they are correct. If they're not correct, and after all the transmission is over, it will report back the result. Say, oh, you have this many errors, or you have no errors. Okay, and that again, that's done through the sideband messaging. And based on that result, that the pair of UCIe interface, UCIe module will know that, oh, the data transmission works at this particular state or not. Okay, so RX initiated pretty much the same, just that it's initiated by the receiver side, the partner side. Okay, and this is just a glimpse of what our finite state machine model looks like. So it's a big case statement that will go through these states, and each state will describe the output that it has to produce and what's the next state going to be. Sometimes it will enable a sub FSM by asserting an enable signal, and wait until that sub FSM says it's done, and because by monitoring the done signal. Okay. And today we'll focus on the MB train part, which perform most of the calibration that we're going to talk about. MB training performs a lot of calibration, like and they're signified by these names. So val stands for valid, data stands for data. So val Vref, data Vref means you want to find the optimal reference voltage level for the valid and data. Speed idle is a step for setting the data rate. I'll come back to this. And after that, you start. So the first step was done at the lowest data rate of 4 gig transfers per second. And after that, you start transmitting at the higher data rate if possible. That's adjustable. First, you find the timing between the data and clock that can sample the center of the eye. Also, you do another reference voltage adjustment at the higher data rate. And these are for the valid. You do another thing for the data. And there's additional step called RX skew, which means that up to this point, the clock to data timing adjusted as a whole collection. So you have a 64 or 32 data lanes between the modules, depending on the package type you have. And all of the data lanes timings are adjusted, equally. But at this RxDSkew stage, you now have a chance to adjust them individually, lane by lane. That's RxDSkew. And once that is done, our specs is worried about the center point being disturbed, so it performs another the timing adjustment. And then link speed stage, it says, oh, now everything is calibrated. Let's make sure that it works at this speed. And depending on this result, if it's successful, say, oh, it's okay to start operating here at this data rate, given these settings for the Vref, timing, and so on. But if it says fail, then it goes back to the speed idle state and will downgrade. It will downshift the data rate and go through these training steps again, see if it can work at the next lower data rate. And it will continue until the result becomes successful. Okay. So here's another view on those steps that I mentioned with the sequence. It's basically a linear sequence with a possible loop in case you have to adjust the data rate. Okay. So it's a lot of adjustment, but actually there are only three categories. One is calibrating the Vref, the reference voltage. The other one is calibrating the timing between the data and clock, or valid and clock, finding the center of the eye opening. And the last one is the RxDSkew. So we'll mainly talk about those three things. Okay, so starting with the process of finding the optimal Vref. So again, I'm not claiming this is the best way. This is just a one way. So our goal is to find a center of the passing window within a certain range, covered by the min and maximum. Okay, so we are so for example, these control code is adjusting the reference voltage. Okay, and we're expecting there is a certain passing range, maybe in the middle. It doesn't have to be in the middle. It could be, in one side, without the failing region on the right, or maybe on the other side. But we are assuming there is only one passing window in the middle. Okay, and our goal is to find the center of that passing window. And we do this by performing two search steps. One, we start from the minimum value of the control code and increment it one by one until we find a value that gives a pass result. Okay, so once we find a pass, we stop and say, oh, that's a boundary 0. Then we start another incremental search starting at the maximum value and now decreasing the value one by one until we find the passing point again. Okay, so we call that a boundary 1. So basically, we're looking for the lower bound and the upper bound of the passing window by walking from the extreme side, the minimum and maximum point values of the range. And we're assuming in the middle, it's all pass. And based on that assumption, we choose the center point as the average of those two boundary values. Okay. So this is described in our finite state machine model. This is the simulation result for a data Vref, finding the Vref value for the data. So it's a very long simulation. It's like 20 microsecond simulation. And it takes about 10 minutes, 15 minutes with XMODEL. And what you see is that there's a big part where you see a lot of activities. And it performs about 8 of them, I guess. Okay. Well, I should start with initially, the logical layer will use the sideband transceiver to exchange messages with the other UCIe module. To say, oh, I'm going to perform data Vref calibration. Get ready. And then it'll start the series of point tests, which are actually given by these activities. And at the and each point test is performed using a different Vref control value. So in the first search, we'll start at the minimum value of 0 and repeat the point test as we increase the control code. And once we find the passing point, we stop. Okay, and then we perform a second search. We start from the maximum value and decrement it until we find the passing point. Okay, now with those two search process, we found the lower bound and the upper bound of the passing range. And then we determine this optimal center, which is the average between the two. And then finally, exchanges these sideband messages, say, oh, the data Vref is complete. This is more detailed waveform inside each point test period. So within each point test, you also exchange sideband messages at the beginning, at the end. And this is the more zoom-in picture of the data being transmitted through the channel and give it a particular Vref voltage. Okay, so this is what I'm talking about earlier. So you see that the majority of the period is occupied by the sideband, communication period. So a lot of the period is occupied by sideband communication. So it is worthwhile to turn off the clock for the main band during those times. It will save a lot of power. I don't know if you care about the power dissipation during the training, but if you do, it will save a lot of power. But actually, it will also save, speed up simulation. Because if you have those high-speed clock keep toggling during the sideband exchange period, well, that's going to impact some the simulation speed. That's actually one reason why I turned it off. Okay. So I said the majority of the logical layer are FSMs, and it's a really giant, big FSM with a lot of states, a lot of transition. Well, maybe not too complicated, but still, it's a lot of states. So we want to make sure that when we run a simulation, we ran thorough simulation that cover every states in the finite state machine and also cover every transition between the states. And you can do so using the SystemVerilog coverage feature because XMODEL is SystemVerilog. Okay, and here are some of the examples excerpt from our modules measuring the coverage. For example, it defines the coverage bins in listing all the states. Sometimes some of the weights only are applicable for the main module. The other states are only applicable for the partner module. And we also define all the transition between the states, the possible transition between the states, so that we make sure that our simulation are exercising all those transitions. And these cover group in SystemVerilog are defined in a separate module. They're not embedded in the actual finite state machine module. So that, once everything is verified, you can throw that model into a synthesis tools to build the chip. To enable these coverage checking, you can simply use the feature called binding SystemVerilog. That is, you can add additional module inside another module without actually instantiating inside that module. Okay, you can bind or unbind depending on use. It's a very nice feature. When you do it, your simulation will report something like this: say, oh, we have measured the coverage for this particular FSM, and the coverage was 100%. I think we actually maybe have gotten results. Oh no. Oh. Yeah, we did. Okay. So there was a little delay. I don't know why. So you see that we have run 50 microsecond simulation, finished in 7 minutes for that calibrating Vref for the valid. And we see the coverage report that says 100%. Okay. For the other part, so we're almost done. So hopefully people can still stay around to see the finale. All right. So another test is, let's see. Another calibration we have to perform is finding the optimal timing. So you're adjusting the timing between clock and data, or clock and valid. There are separate steps for doing these calibration. So as I said earlier, these timing offset between the data, clock and data, and clock and valid are adjustable by controlling the amount of shift through the FIFO. It can support both the positive shift and the negative shift, and also adjusting the phase interpolated code ranging 0 to 60, from 0 to 63. Okay, so we have a rather wide range of code, and you're looking for this one opening, and you want to find the center of that opening. Okay, so it's possible for us to use the same approach as before, but the problem there is that it will take a very long time to find this opening just by doing a incremental search using single steps. So to make this calibration a little bit faster, we use two-step approach, combining a coarse step search and a fine step search. So in a coarse step search, it's kind of like the incremental search, just that we're using the larger steps. We use a step of 8, assuming that when there's opening, the opening is at least 8 wide, 8 steps wide. Okay, that's about a quarter of the UI. Okay, so we use a step of 8 to find the passing range, and we'll say, let's say we find the minimum value of min c underscore c and the maximum value of underscore c, and then we'll transition into a fine step search, where we we narrow down the search range, and we conservatively we set the minimum range of the fine search to be min underscore c minus 7, because maybe the last coarse step just missed the passing point. And then the maximum range is the max underscore plus 7. Again, conservative thinking. Okay, and within this narrow range, now we perform another incremental search, the same search that we did before, using a step of 1. Okay, and again, the center point can be found by the minimum and maximum range of the passing range. Okay, so here's just a simulation waveform of a data train underscore center calibration, first performing a coarse search and then performing a fine search. So again, it's a very long simulation, about like 70 microseconds. So each of these spikes indicates a single point test. So each point test is actually transmitting about 4,000 data. So we can see this, the time scale here. Yeah, this is a zoom in waveform of one single point test, especially at the end of the calibration. So after the point test, it had decided it is a pass. So with the maximum value and the minimum value, you can compute the average and find the optimal center of the passing range. And just like in the other one, we can also measure the coverage, and 100% coverage is good. Now, the last one I want to cover is the RX D-skew. So this one, there is an additional D-skew buffer for each data lane that you can control the skew for the individual lane. So the purpose of this step is to calibrate the skew for each lane individually. So nice thing about this is that we can use the same search algorithm, so we can recycle our FSMs, and all lanes actually calibrate at the same time. They can all do their own calibration. Of course, you need some coordination, but this can be done. So here's a snapshot of the waveform. So we are running a series of point tests while changing the skew value for the different lanes. So different lanes may have a different passing range. So for example, lane 0, it found the upper bound over here. It found the lower bound over here. And then it's already done, but it is waiting for the other lanes to finish. And when they're all finished, it's producing the optimal value. Now, the lane 4 is also doing the similar search. It's finding the different bounds, and I guess it finishes last, and it produces the center point. Now, lane 8, lane 12 has a similar operation, and this demonstrates that you can perform simultaneous calibration on all these lanes, which shorten down the calibration time, which is very important in the real application. Again, you can verify, you can measure the coverage and verify that's 100%. Okay, now you can put all these little FSM together or little steps together and complete the MB train process, which goes through all the calibration steps as I mentioned. And then this is a one giant FSM, still not the whole thing. For this simulation, we can recycle all those little modules that we built to measure the coverage for the individual small FSMs, so that while running the simulation, you want to make sure that we are covering all the states of all the individual finite state machines. So here, this bind statement, shines really beautifully because we don't have to copy and paste the same code. We can just grab the same module and use it in a different setting. One additional thing is that now this MB train process will involve the change in the data rates. So when at the last state, which is called the link speed state, if the results is not satisfactory, it will go back to a speed idle state and downshift the data rate and redo the calibration. So we want to make sure that we are covering all the states and its transitions at each and every data rate. Okay, so to do that, we used another SystemVerilog feature that can define cross coverage. It means for each and every data rate, the states of the finite state machines or the state coverage of the finite state machine are treated differently. So you want to cover all combinations between states and data rate, or state transition and data rates, to make sure that you're running really a thorough verification. So we ran it, and then we found that the link training completed successfully, yay! And turns the link into an active state, which means it's ready to transmit real data. But when we measure the coverage of that simulation, a lot of the FSM only reached 50% of coverage. And it has to do with the fact that the transmission was too successful. The training was finished without any speed downshifts. Like, it was happy with 32 gigatransfer per second. Didn't find a need to downshift the data rate. But to achieve, well, that may be good in real life, but to achieve a full coverage, we would like to actually create a scenario where the finite state chain finds a need to downshift the speed, maybe all the way down to 4 gigatransfer per second, so that it can exercise all the transitions in the middle. And if there's any bug that we haven't seen, it will uncover that. Yeah. So what we did is simply we just made the channel worse, and we did it by adding additional filter that introduced another channel loss. This is one way. There could be another way. You could just use a worse channel model, I guess, but just added one more pole in the channel response, like pole at 1 gigahertz. And then simulation, of course, run much longer because now it's doing more training, but we were able to reach 100% coverage. Okay, and I want to tell you that in the process, we have actually found a bug that from the part that we didn't exercise. So I want to emphasize that using this kind of advanced techniques to make sure your coverage, your simulation is thorough, is very, very important. Okay, and it's also interesting to see this kind of graph, which shows how the coverage is increasing over time. Because for this example, we were able to reach 100%. That's very lucky. Sometimes you may see a plateau, like you reach 70%, but it doesn't increase any further after that. And you can, using this graph, you can see when it reaches a plateau, when it saturates, and you think about what happens there, and how you modify your test bench to achieve a better, higher coverage. Okay, so for a few remaining slides, I just want to flip through some of the additional results we can get after the link is calibrated. Now we have an electrical layer combined with the logical layer that performed full calibration. So we're talking about this UCI link operating in the optimal condition. So this is the eye diagram after the training. It found the optimal reference voltage level, which is around 350 millivolts, which is not exactly at the center because of the digital quantization, but it's close enough. And also for the timing calibration, that was successfully found the center point in the middle. And this is the additional one, is that we deliberately changed the the voltage offset. So we just added a voltage offset in the channel that will force the calibration to find a different Vref value. And we change the offset and see whether the reference voltage tracks it after the calibration. And luckily, we found it does, and verifying that the calibration is working properly. Similar simulation while changing the timing offset. So we're adding deliberate delays in different lanes, and see if the phase interpolated code combined with the shift code will do the found the calibrate will be calibrated properly. So as the delay changes, we found the total delay code, which is a combination of the shift and phase interpolated code, is moving in the right direction. Okay, once the link is calibrated, we can measure now the timing margin using this BER bathtub curve, as well as the voltage margin. Okay, again, for this, we are using the XMODEL statistical simulation capability. All right, well, that's been almost a 2.5 hours webinar. I'm so sorry for going too much over time, but I appreciate it for those who stayed around. Let me quickly summarize today's webinar, and I'll address some of the questions and questions. So today, I presented a SystemVerilog model of a UCIe PHY that's made of the 2 sublayers, electrical layers, and the logical layer. And the electrical layer are mostly analog circuits, and that are modeled in SystemVerilog using the XMODEL primitives. On the other hand, the logical layers are a bunch of digital logic, mostly a digital finite state machine, and they are modeled in the Verilog RTL, the pure Verilog RTL, so that you can synthesize for the implementation. And as I said, the main goal of this webinar is to demonstrate that, for this UCIe PHY, which is a big combination of analog and digital circuit, you can use XMODEL to model those analog parts in SystemVerilog, so that you can perform a very fast and accurate simulation of this complex analog and digital systems, all in SystemVerilog. Okay. And hopefully you get an idea that, hey, within this simulation platform, that's the SystemVerilog with the XMODEL plugin, I can run both the analog verification task as well as the digital verification task. Using the same model. Maybe you can do both in the same in the given test bench. For analog, for verifying the analog part, we see a lot of examples measuring the AC or DC transfer function of the circuit, and we also saw some noise-based analysis for statistical analysis, like plotting the eye diagram is actually one of them. But we also see some more advanced ones like measuring the BER bathtub curve for the voltage and timing margin. For the digital, although today I only showed one part of it, which like measuring coverage, you can easily see that since everything is based on SystemVerilog, you can also do other things like assertion checks, random directed tests, maybe more advanced test benches using the UVM. Those are all possible. And again, don't forget that when we ran the final simulation, we included everything that we discussed today. Okay, so that's it for now. Let me see if there are any questions. This is a question from Koichi Yamaguchi. Can we simulate simultaneous switching noise or interaction with the power delivery network by using XMODEL? Whoa. The answer is yes. For example, simultaneous switching noise, you can add, you can add a little inductor between the source, the ground node of your driver and the actual ground. And since XMODEL simulates all the currents in this circuit level model, those change in the current will cause a voltage drop across inductor, which is the effect of the simultaneous switching noise. It is also theoretically possible to model the power delivery network, but I did give you a warning, heads up warning that, every time you make the models more complex, it's going to have impacts on your simulation speed. So it is possible. Simultaneous switching noise, it is actually done by some of the people. But power delivery network is a very, very difficult problem. So if you have a massive RC mesh describing a power delivery, describing a power delivery network, and you want to see every single voltage on each node, that's going to be a daunting task. Let's see. Another question from Koichi. What is the typical approach to capture the non-idealities of the phase interpolator matched to the real schematic in XMODEL? That's a good question. So on the fly, I can think of a few non-idealities. One of them is the basically nonlinearity as a DAC, because the phase interpolator is a digital to analog, just that the analog output is a phase. So as the control code increases, your output phase may not change in a uniform steps. So you can easily model that. For example, we had a D to A converter, the DAC primitive between the digital code and the actual weight that goes into the interpolator primitive. So that can have a non-uniformity. So that's one way. The other non-linearity I can think of is some second order effects due to the finite rise and fall times. That one is not being currently modeled in our models right now because we're treating those output as a pure digital. So this is 1 and 0. But if that's important, you can turn it into a finite rise time, fall time signals, like we did in the DCC. Another non-ideality I can think of is noise. The phase interpolator can add jitter onto the input clock. That one is easy. So there is any block that delay. Okay, let's say you can use delay X bit or delay to clock primitive. Those primitive that can produce delay. They also have additional parameter for adding phase noise or jitter. So by doing it, you can also add jitter. Let me know if that list is not enough. Okay, another question from Xiaobin Xu. It seems XMODEL is implementation dependent. I don't know. How could we include the real non-ideality, parasitic power grid? Furthermore, what is the simulation tolerance impact, especially for high-speed signals? I disagree with the statement that XMODEL is implementation dependent. It's you can do whatever you want. That's actually different from the actual circuit design. Let's say during circuit design, you only have to use the transistor provided by the foundry, and you're supposed to work within that boundary, right? But with XMODEL, it gives you a capability of expressing what you want to build, regardless of what you can do with the technology. So you can describe a functional model or behavior model that gives you the ideal behavior. I think that's a huge boost in your design process. But when it comes down to exactly modeling the actual behavior of the circuits, analog designers, they typically worry about a lot of non-idealities. They want to make sure that all the non-idealities are captured so that when you run one simulation and when it gives you a satisfactory result, then you're done. You want that. I'll tell you the bitter truth that is never going to happen. If you're looking for a super fast spice that you throw everything in, run single simulation, you look at the result, and you verify everything, you're dreaming. And that day is never going to come. Even for digital, who are is addressing a way bigger circuit than analog today, they're not doing that. So they never expect a single simulation to verify everything, including all the non-ideality. What they do is they break the whole set of non-ideality or set of verification tasks into a set of small tasks, and they do it one by one using a method that's most optimal for each task. For timing analysis, more cross-couple analysis, power analysis, functional verification. All those verification tasks are treated individually and done by individuals. So unfortunately, my answer to that is I'm not saying XMODEL is not capable of modeling non-ideality, but I'm saying you want to do it one by one. Say, oh, what is the impact of non-ideality of the phase interpolated non-linearity, for example, and see how much of the range you can tolerate. And then you move on, start adding one by one, see if your circuit is robust to these incremental non-idealities. I strongly believe that will actually give you tell you the final answer much in a quicker time, trying to rely on just a single simulation, especially with the power grid and parasitic. I know where that's coming from. That's like you want to do a parasitic extraction simulation for the entire chip. Well, truth is, even digital people don't do that. There's another question about Linux command to update our XMODEL module installed. I guess you are an XMODEL user. Thank you for attending this talk. I think the way to update your XMODEL release will depend on the setup at your site. So just talk to me afterwards. Depending on who you are, where you work at, I'll give you a proper answer. All right, I'll wrap it up now. Thank you for attending this very long webinar. I hope you enjoyed it. And I mean, although I gave you a disclaimer that these models may not be accurate, or we don't guarantee them to be accurate, but I do hope they could serve as a good start when you do a design for either the UCIe electrical layer or the logical layer. All right, again, thank you very much. Bye-bye.